Hello everybody, welcome back to Felsefesine YouTube channel. Today we will be going through the IBDP Mathematics AA Calculus second episode, which will be about derivatives and properties of curves. And today we have Ege once again today with us. Hello Ege, how are you?
I'm fine, Burak. How about you?
Oh, I'm also fine. Just trying to struggle with the IB as the mocks are also coming through.
It's the same for us.
Yep.
My fellow IB friend.
Exactly. So, are we ready to solve today's questions and concepts?
Yes.
I'm
ready.
Yep. I hope our followers are also fine. We will be very glad to hear from you, your questions. And again, our class notes will be shared with you for Felsefesine users on our website. So please don't forget to subscribe there. Okay, Ege, do you want to start?
Yes, why not? Let's start.
Okay, rule of differentiation. Let's go.
Okay, so guys, differentiation is the basis of calculus, and it's really important to understand it. Okay, let's give it a start. Differentiation. What does differentiation mean? Maybe if our viewers know it, maybe they can give the answer below. But let's answer it for them. Differentiation gives us the gradient function of a function. For example, let's say if we have a function fx, and if we find the derivative of it, then whatever number we put in the place of x, whatever value we put in, it is going to give us the gradient of it at that point. You will know what I mean when we show you the properties of curves. And it's going to be in this video, so no problem. It's going to be more clearer. Okay, so this is the first example. You don't have to solve every example, but this one is a important one. So this is our rule. We have a function fx, and it's equal to x to the power of n. And when we do its derivation, and this is going to be f prime x, and we call this prime, divided by Well, can you make it bigger, please?
Yeah, sure.
Can you zoom out?
Yep. Is it fine? No?
Is it delayed? Yeah.
I guess so.
Let me take a look. Yes, it's perfect.
Okay.
Okay, so this is f prime, and you have to write it f prime. If we write this, then when we take its derivation, f prime x happens, and we put in the power here times x to the power of n minus 1. This is our very first rule. It's important to remember. Let's mark it. I also wrote it here, you can see here. Okay, so let's solve our first example. In our first example, you can see find dy dx, and dy dx is actually the gradient function of it. Like it's like y prime x, but we say prime, so we have dy over dx. Okay, we have 3x to the power of 4 plus blah blah blah, and let's solve it. Okay, so we have a power 4 here, and let's put it here. Power 4 happens, but we don't touch the 3 here. It stays. So we have extra 3 here, as you can see. Yeah. And we reduce the power by 1, and it occurs 3. And it's the same for others as well. But as an exception, and this might confuse you, but let me explain it. Okay, so we have 7 times x to the power of 0, but we cannot reduce it by minus 1 because power goes here as 0. So constants will be 0 always. And remember it. Do not memorize it. Just remember the rule of differentiation, and you will be good to go. And at the end we have 12 times x to the power 3 plus 6x squared minus 10x, and this is the first rule, first example. Okay, let's go down and let's take a look at right, could you go down a little bit?
Yeah, I
Yes.
did.
I'm going to solve example number 3. It is y is equal to 7x minus 4. Okay, so let's take a look at this. Actually, we can write this function as y is equal to 7x minus 4x minus 1 plus 3 times x minus 3. And this is going to be the case. It's not challenging. You just have to remember your exponential functions knowledge. Okay, let's put them. Okay, let's take their derivatives, and this the first one is easy. It's going to be 7, and x will be the power of 0, and it's going to be 1, and we are left with 7. And and let's pass to the other variable. Let's take a look at it. You have a minus here, right? I think you can see it. Yeah. We have a minus here, and when we reduce this minus 1 from 4 times x to the power of minus 1, we are putting it as a multiplication, and it's also minus 1. And we reduce it by 1, so it's going to be minus 2, sorry. And it's going to be 4 over x squared minus, and we have a minus here again, and we reduce it by 1, and the same thing is applied here. So we are left with this gradient function, slope function. Yes, I think it's enough, Burak.
Yep.
And let's solve. If our viewers are interested in challenging themselves, maybe you can show the good question there without showing the answer,
Yep.
maybe.
Oh, okay.
Okay.
Like this, maybe?
Hello Gülşah hocam. Hello Zeynep, by the way.
Yep.
We are glad to see you here.
Yep, thank you very much for being together with us.
You always view our streams, and we are glad to see you again here.
Definitely.
Okay, if you want to challenge yourself, you can give it a go. The good question. It is dy over dx, y is equal to x square root x minus 4 over x. The answer is given there, but we are going to do some little tricks. Okay. Can you hear me now, guys?
I think it's better.
Zeynep, can you hear me? It's better, right?
I guess so.
All right, let's give it a go. Okay, could you move down?
Is this fine?
All right, that's perfect, yes. All right, nice. So, as you can see, we have square root x minus 4 over x. Actually, we can separate it because they have a common denominator, x. And when we separate them, as you can see, we can find this. Square root x over x minus 4 over x. And when you see this, you can actually apply your exponential function knowledge. And when we do this, we are going to find 1 over 2 minus 1, and you can see that it's actually 1 over square root x. And when we write it by their power, not with square roots, we can actually derive this. How can we derive it? So as you can see, we derive it here. Let's write it. Yeah, we have minus 1 over 2 times x, and we reduce it by 1, so we have minus 3 over 2. is -1, because we have -1 here on the board, and then as you can see, we can write that it is -2. So we simplify it. You can actually write this equation like this. It is basic knowledge, but let me remind you that. Okay, so, and at the end we find that equation. Okay, I think this is very long. Okay, let's pass to the chain rule.
Okay.
Alright. So in chain rule, it's simple, but we have to be very careful with it. Okay, so what is the rule? If we have y is equal to g, u, and g is a function, by the way, where f is where u is equal to fx, then we can see that it is dy over dx is equal to dy over du times du over dx. Let's give it a quick example, okay? And then if we actually see this function here, we can do it by this way. Not, you don't have to memorize this, okay? But let's take the derivative of the fx over to the power of n. Okay? Let's take its derivative first. Okay, let's take it. This n times fx n minus 1 to the power of n minus 1, and what we are left with, we have one more thing here. We have fx function, and let's take its derivative as well. And as you can see, it is a simple thing, but you have to be very careful. Okay, let's see. Y is equal to x squared minus 2x to the power of 4. We can firstly derive, let me write it here with a different color. Okay, y over dx. Okay, so let's take the derivative of u to the power of 4. Okay, let's say u is equal to x squared minus 2x. And let's take its derivative first. It is 4 times x squared minus 2x over 3. Okay, and we have one more thing actually, and we have to take the derivative of x squared minus 2x itself, not its power. Okay, let's take it. It is 2x minus, and as you can see, we can find the correct results. Yes, perfect. Okay, let's pass to the second question. Burak, could you move down?
Yeah, I did.
Yes. Okay. So, when we take a look at this equation, we can actually write the denominator as having the power of minus 1 over 2. And if we take its derivative first, let's choose what color here? Yeah, let me write it here. If we take its derivative, we can see that it is 4 times minus 1 over 2 times 1 minus 2x, sorry, 1 minus 2x to the power of 3 minus 3 over 2. You reduce it by 1, so we are left with 3 minus 3 over 2. And let's take the derivative of the 1 minus 2x itself. Is a different function. So when we take its derivative, we are left with minus 2. That's it. And as a final result, they will cancel each other, and these minuses will be positive. So we can see that it is 1 minus 2x to the power of minus 3 over 2. That's it. That is easy. Okay, let's not solve the other question.
Yeah. But again, our followers can reach this question from our Felsefesine website, right? All the time.
Yes,
Available.
I was going to say that. We don't have to solve every question because we are doing a revision here, and we are most likely able to solve most of these questions. So let's try to be quick and teach you very important concepts. Okay, so we have product rule. Product rule is really important, and these questions questions about product rule can be combined with chain rule. So let's learn it thoroughly. Okay, so let's see what it is, and it's actually given in the formula book, so you don't have to memorize it. But as you solve questions, you will remember it, so you don't have to look at formula book. So let's say we have a function fx, and it is equal to ux times bx, and they are functions both. U and v are both functions. And as you can see, when we take its derivative, firstly, we take the derivative of u prime x times vx, and we don't take the derivative of v, plus we take u as its function, as it is, and times v prime. It doesn't actually remember if you take the derivative of the u or v, because we are just adding them up. That's it. Okay, let's solve the next question, next example. Okay. As you can see, guys, it is given that we have x squared times x squared times 2x to the power of 4. We have to use chain rule and also product rule. Okay. Okay, when we use, let's take the derivative of x squared first. Okay, and we take its derivative, we can see that it is 2x times it is x squared minus 2x to the power of 4. It stays, we don't touch it. And plus, we don't touch x squared here. And let's take the derivative of second function. And we take its derivative. Firstly, we take the derivative of the outer function, the x squared minus 2x to the power of 4. And when we do it, it is 4 times x squared minus 2x, and it is to the power of 3. Be careful, just reduce it by 1. And times, and we take the derivative of the inside function, then we have 2x minus 2. And we have to multiply them, not add them. Be careful, do not confuse chain rule with product rule. It's really important. Okay, I think that's enough. Oh, Burak,
yeah.
we have the gradient of the tangent. I think it's important.
Okay.
Because we never solved such question before.
Exactly. And by the way, please get familiar with this concept, because we will be using it further in how can I say, implicit differentiation part. So it will be important to understand this concept.
Yes, exactly, and we will use it in properties of curves.
Exactly.
You will encounter these kinds of questions a lot, but let's give it a initial practice. Okay, it says find the gradient of tangent to, not to as number, but okay, as you can see, this function is given, and the point is given, as I told you in the beginning of this video, is at the point of x is equal to minus 4. When we take the gradient function, we have to find the gradient function first. Okay, and if you draw any, let's say this is a function. Okay, this is a function, and let's pick this point. It is minus 4. And if you draw a gradient, if you draw a tangent to it, then you can find its derivative at that point. So that tangent is this, that gradient. Okay, let's take the derivative. First, we don't touch the square root. And when we take the derivative of it, it is 1 times square root 1 minus 2x plus we have to take the derivative of, we have to use chain rule. And it is, we have to take the derivative of the bigger function, okay, 1 over 2, and then this times x, because we don't touch the x here, and we take the derivative, I mean we reduce it by 1, as you can see it is minus 1 over 2, and times we take the derivative of the inside function and it is minus 2, and when we simplify it, we are doing this simplification here. I don't want to tell you how to do it. Let's not waste our time. And as you can see, we are left with this equation. And this is the important part. It is gradient function. Whatever value you put in that function, you are going to find its slope at that point. And we had minus 4. Let's put minus 4, and then we are left with 13 over 3. That's it, guys. That's it. It is simple, but it takes time. It takes effort.
Yeah. Yes.
Okay, let's
Quotient
pass
rule.
to the quotient rule. It is the last one, and then the Brock. Oh no, it's not the last one. We have last of rules. Okay.
Yeah.
Then we are going to apply these rules to different functions, like exponential, trigonometric. Okay, let's go. Okay, so we have a function qx, and it is equal to ux over vx. And when we take its derivative, and it's also given in formula book, let me write it, given in formula booklet. And when we take a look at the formula booklet, we can see that it is u numerator. We have to take derivative of numerator first, and times we don't touch the vx here, and minus, and this actually matters which one you take first here, because we are not adding up, we are subtracting. And then ux times v prime, the denominator one, is taken as derivative, the second part. And in the denominator of the prime function, you can see that we are taking the square of the denominator, vx square. Okay, let's solve the first example. And when we take a look at the first example, it is actually simple, but let's solve it by ourselves, okay? And I already wrote it there, but I want to write it again. Okay, I want to solve this question with you guys. Okay, so what the equation say, what the formula says us, it tells us that we have to take derivation of the first one. Let's take its derivation. And when we take its derivation, it is 3. And you will be more familiar with how to do the derivations in your head as you solve more questions if you are new to the concept of differentiation. Okay, so we don't touch the denominator here. It is times, by the way. Minus, we take the derivation of x squared minus plus 1. When we take its derivation, it is 2x, but we don't touch the numerator, so let's put our numerator, it is 1 plus 3x, and over, it is x squared plus 1, and what I'm going to do here, take it square. That's it. That's it. That's the thing we should do. Okay, so we have a very long question here, and let's go through it quickly. Also, I know Brock is eager to teach you his concepts also, so let's not make him more impatient. Okay, so this question is a bit long, but let's take our time, alright? Okay, so we don't touch the, as you can see, I will mark with the green, not green, I will choose, I love yellow, I love the gold. Let's see, we don't touch the denominator. Okay. And then we take the
Yeah, your voice is going further and further. Yeah, fine now. It's fine.
Is it good now?
Yes.
Is it better?
Yeah, I think it was better now.
Okay. Let me switch my microphone. Okay, I think it's better now. Okay, so as you can see, we already taken its derivation, and then we reduce it by 1. X to the power 1 over 2. And then when we pass to the second one, we don't touch the square root x, but we are taking the chain rule. Okay? And then when we take the chain rule, it is its power is minus 2. So it is going to be minus 2 here. And then when we take the that it's not, sorry guys, its power is not minus 2. We take it as it is, not as, we take it as it is. Do not assume that it is 1 minus 2x minus 2 in the quotient rule. Please don't do that, I made a mistake. When we take the derivation of inside function, we can see that we find at the end this one. But they have a common point here. It is 1 minus 2x. And we can actually take it as a common factor. And when we do it, as you can see, we are left with this equation below. And when you just add them up, you are left with 6x plus 1 minus 2 square root x and blah blah blah. If IB gives this kind of question, not the questions that we solved together at the first part, because they were just for the purpose of teaching you. But IB asks about these, like taking common factors, simplifying them. IB wants to test your algebra knowledge. So just be careful about it and solve as many questions as possible on this topic. It is not very challenging, but it's doable, guys.
Yeah.
If you show enough like algebraic knowledge, if you think about the question and do it carefully with by being careful about the signs, like negative or positive, then you will be fit to go.
But try to remain as analytical as possible. Do not skip any steps, show your understanding clearly, and approach the question cleverly.
Yes, and do not rush the questions, please.
Yeah.
I know we don't have much time. We have 1 minute per mark, but if you miss one question, then it's going to affect the others as well. So do not try to rush. Okay, so let's learn derivatives of exponential functions. Okay, Murat, we have 2 exponential functions. One is your Euler's number, and we made a presentation of it while we were at school. It was good old days, there was no corona.
Exactly. Yeah, right.
Okay, so if the rule says, and it's actually in the data booklet, if we have a function fx and it's equal to e to the power of x, and its derivative will be the same. But if we have e to the power of fx, and if we take its derivative, then it's going to be e to the power of fx, but we multiply it with f prime x. And this is the logic of chain rule. If you know the chain rule well enough, then you can solve these questions without memorizing or even looking at the data booklet. Okay, actually this second rule is not given in the data booklet. You have to know it by heart. I mean, just remember the chain rule here and solve these questions.
By the way, Ege, shall we remind our followers about one more thing about using the data booklets? So, especially in the calculus part, if you are given a formula for the calculus part, and it says, for example, let's say derivative of sine x is equal to this one, please remember that x actually means fx. This is another function. So just assume that this part has to be derived as well. So for example, if it says e to the power x is equal to e to the power x, this means that actually we have to multiply the result with x derivative as well. So this is a common thing that most of the IB students may be confused about. But please remember that if you have something remaining from the chain rule that you have to derive, please derive it and multiply it.
Yes, thank you for the reminder, bro, and it's an important concept. Okay, and it's actually very important to use the data group, especially for calculus. Okay, so let's solve the first example. So in the first example, we have 2 times e to the power of x plus e to the power of minus 3x. We have an x here. So what does it mean? We are going to use check. Okay, so so the first one, 2 times e to the power x, it's going to be the same. We are not going to touch it, because when we take a look at the formula, I mean, it's not. You don't have to do anything to it. But in the second one, we have to change it. And firstly, we have to take the derivative of the power function, exponential function. And when we do it, it is minus 3 times e to the power of minus 3x. And the e's do not change. The Euler number does not change. Just if you remember this, it's okay. Alright, and let's solve. Let's not solve it.
Okay.
Let's leave it for the viewers.
It's on felsefesine card again.
Yes, and you can access it by reaching the felsefesine.wixsite.com, and you grab your felsefesine card and reach our exclusive content there. Okay, so the second group, we have another exponential function, and it is any number to the power of x. It's not actually, it's not any number. A cannot be minus 1. Let's remind it. I forgot to put that. It should be more than 0. More than 0. Okay, so the formula tells us that dy over dx is equal to a to the power of x times ln a. And if we have a function instead of x, only x, then it is going to be a to the power of fx times ln a. A doesn't change, but we, as an extra, we take the derivative of the fx. Okay? So let's solve the first example. Let's not solve the first example, it's very easy. Let's solve the harder one. Burak, could you move down a little bit?
Yep.
And this is the point where we use the product. These kinds of questions could come up in IB, so let's talk about it. Okay, so let's take the differentiation of the variable dx. And let's take the derivation of the x to the power of 3, x cubed. And its differentiation is 3 times x to the power x squared times, we don't touch the 6 to the power of minus x, but plus, okay, so we don't touch x cubed, okay? But if we take the derivation of 6 to the power of minus x, firstly, let's put 6 minus x times ln 6. We take the natural logarithm of the base, and times we have to take the derivative of the power function, exponential. When we take it, it is minus 1 actually, and at the end we are left with 3x 6 to the power minus x plus minus x squared, x cubed times 6 to the power minus x times ln 6. Then that's our answer. That's it. This is it for exponential functions. And if you have any questions, you can write them below. Burak or I could answer it. Okay, and I think it's Burak's turn. I know Burak has been waiting for this moment.
Okay, so first let me adjust my voice a little bit. Just like this. I think it's fine. Okay. Yeah. I hope my voice is all fine on the live video. So, okay, derivatives of logarithmic functions. Please just remember that in IB you are asked to understand two concepts about logarithmic functions. The first one is ln x and the other one will be log x. So let's start with ln x. We will be doing a small u substitution at this point. Okay, let's see. I will choose this color. So we said y is equal to ln fx. Once again, I want to remind you that in the IB data booklet, x stands for fx. That's why I wrote fx. Now let's say u is equal to ln x. U is equal to ln x. Now, what happens? I substituted with sorry, this is not ln x. This is fx. Okay. This is fx, and as we substituted, we see that it is equal to y ln is equal to ln u. And hence when I want to have dy over dx, I am using the rule and dy over du from chain rule times du over dx. Now, when we look at dy over du, it is 1 over u, and du times dx is du over dx. Because we know that u has to be derived once again, since it is concluded in the chain rule, and ln, when we use ln, the derivative of ln is always 1 over fx, okay, 1 over fx. Hence, we can conclude that ln fx has the derivative of f derivative x over fx. This is all.
I don't want to interrupt you. We have less than a minute for Zoom.
Oh, can we switch it right now?
Yes.
Okay.
Our viewers, could you wait a little bit?
Yes, just a second. Just a second. This is because of Zoom.
Please do not leave the meeting. I know that we don't have many viewers, so I don't think they will. Okay, let's switch.
Okay.
Mamro.
Hoş geldin kankacığım.
Hoş bulduk ya. Yardırıyoruz ya.
Kankam vallahi güzel gidiyoruz ya. Allah'a şükürler olsun. Şu Zoom olayımız da olmasa. Yani yine çıktı.
Have we started?
Yok. Biz hala live videodayız değil mi? Neyse devam edelim. Artık zaten iyice samimi olduk. O yüzden bizi duymalarında hiçbir sakınca yok. Tamamdır. Geri geldik. Okay, let's go. Let's go back to English. Everything is fine. Yay. Good. Ege, are they seeing our screen right now? They do, right?
Yes, they can, I think.
Okay, nice. Okay, nice. So, Again, I gave 3 examples for ln x, 0 level, middle level, and how can I say, hero level. I will solve only 0 and hero levels. First one is 0 level. Let's see. Find the gradient function of fx is equal to ln x. So we also said in the rule that f derivative x over fx. Hence we can say that dy over dx is equal to 1 over fx times f derivative x. What is the derivative of x? It is only 1. So 1 over fx. What was our fx? It was x. Hence we have 1 over x. This is all. When you see ln x, you just take what is inside of the parenthesis to the denominator and 1 over the fx. This is all we can say. So this is the middle level. Again, I will not solve it. I will go with the hero level. So again, solve this question today. I wrote it, and this is actually literally a hero level question. So let's see. Find the gradient function of fx is equal to x squared ln 3x squared over x minus 1. We have to act cleverly while solving this question. We have to recall the product rule. This is the first thing that we have to remember, because we see that we have multiplication over here, and we will just solve them in this way. Now let me just clear that part smoothly. No, it doesn't happen. Okay, no problem. So for v, meaning the ln parts, we have to understand the concept that while we were talking about ln, we said ln a over ln b is equal to ln a minus ln b. This is very important, because now I just want to write it in the form of fx is equal to x squared times, in the parentheses, ln 3x squared minus ln x minus 1. Nice. Now, it is right the best time to spread this x squared by expanding it inside the parentheses. So x squared ln 3x squared and a minus x squared ln x minus 1. After doing that, what do we see? Again, can you see the product rule? But it is done twice. We have 2 terms here. So we have to do it twice. The first one, you can remember the formula from here, the product rule. It is given right over here, so you can just remember it directly. Okay, derivative of x squared 2x times directly v ln 3x squared plus this time directly u x squared times derivative of ln 3x squared, which means that, so do you see now, I said 1 over 3x squared, since it is in ln, 1 over my function in the parentheses directly goes to denominator, times derivative of this function. 3x squared has the derivative 6x, so 6x over 3x squared. Then I do exactly the same thing for the second parenthesis over here, for x squared ln x minus 1. Therefore, I came to here and I try to simplify it a little bit more by doing what? For example, this was x squared times 6x over 3x squared, but this is just nothing but plus 2x. Try to simplify it, further simplification, and we reach this. However, you may see that there can be further simplifications that can be completed. If you wish to do it, you can do that. Because you can see that in the denominator here we have x minus 1. So the other terms should be also multiplied by x minus 1, and it should be written in a more simplified form. This is the whole question with the solution. This is literally a hero level.
This question is really painful.
Yes. Any small mistake can just cost more than that. Because if you make a mistake, let's say here or here, the remaining parts will also be damaged. Hence, please be careful and try to solve those kind of questions, and try to get familiar with the integration of other concepts. In this part, for example, we saw product rule, we saw ln rules, so try to combine them all together. Nice. So second logarithmic function is directly log x. And here is my rule. I said if I have log x, with the base a. Let's say y is equal to log a fx. Again, u substitution. Let's substitute it. For u, let's say fx, and then it will be log a in the base u. Okay, nice. So again, dy over dx will be equal to dy over du times du over dx. I can see that since I have this log means that when you see log directly, write 1 over u ln a. 1 over u meaning your fx times ln a times du over dx. Again, did it remind you of something? Let me tell you what that is. Let's recall our ln fx, right? ln fx. So doesn't this mean log e fx? Am I right? So using this rule over here, my dy over dx would be equal to 1 over fx times ln, what is my base? It is e, right? E times f derivative x. Now did you understand why there is a difference between log x and ln x? Because ln e is already 1. That's why it was given in this form. That's why the rule that we previously discussed was in that form. Just you can understand it from here, just by using log x rule. So the simplified form for log x is f derivative x over fx times ln a, where a is our base. Okay? Everything clear? Let's solve questions. I have two. The first one is pretty easy. Find the gradient function of fx is equal to log 4x. So, sorry, this should be 5, I guess. One of them should be 5. Oops. I guess my OneNote has just crashed, so let's open it once again.
It happens to me.
Yeah.
Very, oh my God.
I wish I had iPad Pro.
And this is the conversation between me and Burak. We want to have iPad Pro.
Any supporters? So
if you want to donate, guys, we are open.
all the time.
So that we can give you a better streaming experience.
Definitely. So we can see that I directly apply the rule that's given here. Since my fx is equal to x, f derivative x will be just 1. So I have 1 in the numerator, whereas over in the denominator I see x, my fx, times ln 5. Why ln 5? Because it is ln a, where a is the base and my base is 5. Easy. Now a more difficult one, find the gradient function of fx log 3 x cubed minus 1. So now I see that my fx is not x only, and it can be derived and it has to be written, it cannot be neglected. So 1 over x cubed minus 1 times ln 3, 1 over, this is fx directly, this is fx, and ln 3, this is the ln a part, where a is the base and it's 3 over here, times 3x squared. Why did we write 3x squared? Because inside the parentheses has to be derived as well due to chain rule. X cubed minus 1, so it is 3x squared derivative. That's all. I hope it's clear. Now it's time for trigonometric functions. I am sure after you start to solve some past paper questions, you will get familiar with them and it will be a reflex of yours. However, I just wrote them in the forms that they are given in the data booklets. So you may look at them at the beginning, but then it will be your reflex. So you will be just directly writing them without looking at the data booklets. So on the left side you will see the function, trigonometric function, and on the right side you will see their derivatives. Let's start. If we have sine x function, it is cosine x. And if we have cosine x, it is negative sine x. So people are asking me how we can just Keep this in mind. You may, actually this is one thing that I am doing. We know that while we were discussing in trigonometry for unit circle, we said that this axis, y-axis, is sine axis, right, again? And we said
yes,
this is cosine x. And we said this is negative sine x. Hence we said this is negative cosine x. The axes are like this for a unit circle. Hence, you can see that if you follow the clockwise direction, d over dx, you can see that d over dx, derivative of sine x is cosine x. Derivative of cosine x is negative sine x. Derivative of negative sine x is negative cosine x. Derivative of negative cosine x is sine x. You can already see them here. Hence, it will be very easy for you if you can just visualize this in your mind and remember it in that way. I say do not memorize. I didn't say memorize them. Just keep that in mind. So now it's time for 10x, right? 10x. We have to use the quotient rule. Why? Because 10x can be represented in the form of sine x over cosine x. So let's say, as Ege explained previously, sine x is u and cosine x is v. Applying the quotient rule, cosine x minus sine x over cosine x square. I simplified it, and it is cosine square x plus sine square x over cosine square x. Again, do you realize the trick? Cosine square x plus sine square x is equal to what? 1.
Yeah, 1. Trigonometric identities.
So this is equal to 1 over cosine square x. Another identity, 1 over cosine square x is equal to secant square x. Therefore, the derivative of tangent x is equal to secant square x. Already in the data booklet, but just to keep in mind, because when you learn how to derive something, you will remember it better, just like in physics. Okay, let's go on with the other trigonometric functions, in which they are represented in reciprocal forms. Cos x meaning 1 over sine x. So cos x has the derivative of negative cosec x cotangent x. To be honest with you, I don't really memorize them. Some of them have become my reflexes after solving past paper questions, but you are given the data booklet, so do not please hesitate to use it. You can just directly look at them and apply the formula, where x will be your fx. Please do not forget that. Secant x has the derivative secant x times tangent x. Cotangent x has the derivative negative cosec square x. Actually, again, I shouldn't really focus on that point that much, right? Because just use the data booklets. Just use the formula.
Yes.
You are given the opportunity. This is not like the national curriculum. This is not like the national curriculum. So just feel free. Try to become more analytical. So an example, just about this one. I tried to compile the forms, different forms. So find the derivative of cosec 3x square. Let's see. The rule for cosec square is actually over here. Let's have a look at it, imagining that we are using the data booklet. Hence, I can see that cosec x, I write negative cosec, in the parentheses I write my function 3x square times cotangent, in the parentheses again my function 3x square times, since it is a function, it is the chain rule. If you have anything left in the parentheses that has to be derived once again, 3x square, our function is not x, has to be derived and written here, cannot be neglected. 3x square has the derivative of 6x, so I multiplied it and found this answer. Clear. Next, derivatives of trigonometric functions. Now, this part may seem very short. As you can see, it just jumps to the next question. However, again, you remember the Maclaurin questions that we solved in past paper. you have to have an sight reflex, okay? I call it sight reflex. For example, it says arc sine x is equal to 1 over root 1 minus x squared. Arc cosine x is negative 1 over root 1 minus x squared, since it's arc sine and arc cosine, just multiply by negative. And arc tan is 1 over 1 plus x squared. Now they may seem like, okay, this is an inverse function, so what to do with this? But when you are studying integration, which is in the next episode, you will realize that you will see things in that form, okay? This is sight reflex. When you see something in that form, this has to remind you of inverse trigonometric functions, okay? This has to remind you of that. You have them in the data booklet. So try to solve questions about them. In Maclaurin part, Maclaurin expansion is a pretty huge concept and it's hard to understand for the senior year of high school for IB students, but you will be using them. Arc 10x, you may have to use that to remove the 10x from the equation, but while doing the integration you will come across that. So have this reflex, gain this reflex. Important, yes, very important.
And guys, if you see such a function that looks like them, just check the data booklet and see which one fits. Because while using integration, as Burak said, I mean, it seems very indirect. I mean, you feel like you cannot integrate it.
Definitely.
And it's actually the arc sine or arc cosine or arc tangent. And I think what Burak said is really important, guys. I think it's going to be really useful.
So please practice that. Please practice that. Second and higher derivation. You can understand it already. I am sure you already know it. Second and higher derivation. This means f second derivative. F dash 2 dash is represented in the form of d square y over dx square, and this means derivative of dy over dx. We already studied dy over dx. Now take its derivative as well. What does a second derivative give us? It gives us the rate of change of dy over dx in according with x. According to x. So this will work in the next parts. Today we will also explain properties of curves as well. In properties of curves, it is just a concept. Second and higher derivatives or the first derivative. So I gave an example over here. Find f second derivative for fx is equal to sine x plus 4x cubed. We have also trigonometric and polynomial part. Let's see. Let's derive it first, just for once. Derivation of sine x plus 4x cubed. Sine x is cosine x. We know it either from the unit circle diagram, or either from your memory, or either from your data booklets. Plus 4x cubed, 3 times 4 times x, 3 minus 1, meaning 12x squared. This is the first derivative. So we said in second derivative, we derive it once again. Once again we do it. Cosine x. Cosine x. So we are over here. Derivative of cosine x gave us negative sine x. Negative sine x plus 12x squared is derived like 24x. So what if? What if? We were also asked higher derivation, meaning f third. 3 dashes. Or again, we can also write f3, right? While talking about derivatives.
Yes. And actually, Burak, I think you remember them. We solved such questions in our classes, but there were some questions that required the knowledge of higher derivatives, which was about mathematical induction.
Yeah, right. I remember that.
I mean, in that part, you have to use your calculus with knowledge in order to prove that equation by using mathematical induction. So this concept is very important. It may seem short, but as Burak said, it is very important.
Nice point. I really appreciate it. Yeah, it's very important. So, f third derivative. let's say we are giving negative sine x plus 24x, so I have to derive it once again. Let's derive it. Negative sine x is derived as negative cosine x, and 24x is derived as 24. I can be asked even f for x. Now I will derive it once again. What is negative cosine x? It is just sine x, right? So if I was asked f5x, I'm going with the higher derivatives. It would be just cosine x. And so on and so on and so on. Okay? It goes to infinity like this. Now, important. Implicit differentiation. Implicit differentiation means a relation that has both, how can I say, x and y together. However, you cannot just simply take one of them out. This is a correct definition, right, again, that I have made?
Yes. I think it's a perfect definition.
So, let's try to understand that, okay? Let's try to understand that. We will use the chain rule for y. So, we will just distribute our d over dx into the relation. I will show it in a second. And we will just derive y just as if we were deriving x. However, now this time we will act like y is our function. It is already our function. Since we are deriving in accordance with x, we have to multiply the entire expression by dy over dx to have only an x as expression, okay? Then we will simplify dy over dx, which is over here, and the problem will be solved. Let's see a question. It is hard to understand from here. So if we were given x squared plus y squared is equal to 9. Now, let's take derivative of both sides. Taking the derivative means multiplying by d over dx. d over dx, x squared plus y squared, d over dx, 9. Okay, let me do that part. d over dx, 9 means 0, right? No problem with that part. Now, d over dx for this part. Let's derive x squared directly. It would be, just a second, did I make a mistake? Yes. It is 2x plus, now y squared. Act just as if it was one of those x's, 2y times. Y is not expressed in the form of x, so we don't know this one. Chain rule. dy over dx has to be multiplied with that, and it was equal to 0. To find the dy over dx, I just simplify it, and dy over dx is equal to negative x over y. Again, shall I solve a tangent expression question? You may remember that this was in the quiz.
Yes, this was in the quiz, Burak. Also, our viewers could see such questions about implicit differentiation on past papers.
And we were just like rabbits.
8 or 9 marks. 8 or 9 marks. It is very important.
Definitely. So an example over here. Okay. Let's say we are asked a question. Find the find the gradient function of, find the gradient of the tangent, or let's say tangent of x squared plus y cubed is equal to 8, let's say, okay, where x is equal to 2. Now let's start solving it. We will say, let's take d over dx for both sides, x squared plus y cubed, and it is d over dx of 8. I know that d over dx is 0, right again? It doesn't have any x inside of it. Implicit differentiation, this is how we call it. So, for left side we will say 2x plus 3y squared times dy over dx. Why 3y square? Because we are acting just as if it was one of those x's, and times dy over dx, since it's not in the form of x. Then we can see that when we just simplify this expression, we come to know that dy over dx will be just equal to negative 2x over 3y square. Hence, we can say that when, let's say, x is equal to 2, okay, x is equal to 2, I will just say 4 plus y cube is equal to 8. I just substituted my x value into my implicit relation, and when I solve for this, I see that, just a second, may I change one thing in the question, just not to deal with complex numbers. I will just say 5, okay? I will just say 5. Let's say this is equal to 5, so y cube will be equal to 1, and therefore y will also be what? 1. We know that we are looking for tangent at 2, 1. We found our point directly on the diagram. Hence, now I have my dy over dx expression. Let's recall it over here. My dy over dx at this point will be, since in my dy over dx expression I have x and y together, that's why I calculated firstly where am I on the point, where am I on the graph. Negative 2 times 2 over 3y, meaning 1 square. What is it? Minus 4 over 3. Therefore, at x is equal to 2, gradient of tangent is negative 4 over 3. Now again, if it was asked a question, what is the gradient function, gradient of the normal to this relation, we would say 3 over 4, right?
Yes, Burak, and we will be talking about it in our next concept, properties of curves.
Exactly. And you can verify this by using your Desmos accounts. Desmos accounts, because our graphic display calculators cannot do those calculations. Okay? So, shall I go with the, sorry, not physics, this is surprise. So, mathematics, mock revision, properties of curves, right?
Yep.
Again, by the way, those parts are great notes. The colors, I like them. They are great. Thank you very much.
Thank you very much.
We can start.
Alright, guys. Let's start, and this is a very important topic. You may ask why it is important. Well, the reason is the IB gives us an equation. It gives us a function fx, okay, any function, and they firstly want us to derive it, okay, and then they want us to find the stationary points, increasing, decreasing functions, and we will be talking about them, like the tangents, and then at the end we draw the graph, and that graph is around at least 4 marks, maximum 6 marks, and you have to label all the increasing, decreasing parts, all the maximum or minimum points, and it's very important. So we have to understand this concept very carefully to solve those questions, and also to gain an insight, to gain more insight into how the differentiation works. Okay, so let's see the idea of tangents. Okay, and as I told you in the beginning of the video, wherever we draw a tangent to the point at a function fx, we can find its slope at that point by taking the differentiation. Okay, so as you can see, I drew 2 functions, and I chose just one point. Let's say its x is equal to 1, and at those points we draw a tangent. Okay, and if we take its derivative, we find a function, and if we put 1 into the place of x, then we can find the slope of tangent at that point. Yes. So let's try to understand it in the example, in the following example. Burak, could you move down a little bit?
Sure.
Please? Okay. So we have a function, okay, and it asks us the equation of the tangent at x when x is equal to 2 and y is equal to 3. Okay. So let's find its differentiation, and we have to use chain rule here. Okay. And when we use chain rule, it is 1 over 2 because we take the differentiation of the u at first here and to here, and then we find the differentiation derivative of the inside function. And when we do this, we can find that it's x over in square root x squared plus 5. That's it. And when we put x is equal to 2 at that function, this is a slope function, guys. It's a different function. So if we put our values there, let's say it's 2, okay, the question said 2, we can find that the gradient of the tangent at that line is 2 over 3. But let's say if it asked us the equation, if it asked us the gradient of the tangent at the point x is equal to 1, we put 1 here, okay, and it is 1 over to the square root 6. That's it. This is the logic. And let's remind ourselves of the straight line topic, where we had an equation for it is y is equal to mx, m is our slope here, plus b, and this is our y-intercept. Okay. When we do it, we can construct such a equation. Let me write it in log. Okay. We know that our gradient is 2 over 3 times x plus c, but we don't know what c is. But in the beginning, we were given the y value, and as you can see, like if you imagine a function and if you draw a tangent, at that point they need to have the same x and y value, right? So we can pull up that data and put it there. Sorry, okay. And if we put y in the place of, if you put 3 in the place of y, then we can see that we find c as 5 over 3. And at the end, we can construct our equation, as I highlight. This is the slope of the tangent. I know that it took a bit long, but it's very important to remember this. Okay, I will not solve the next question because you can find it in the Felsefesi'nin website, but let's take a look at it. It's asking to find the equations of any horizontal tangents. Guys, what does horizontal tangent mean? What does it mean? What do you think?
May I say it again, hocam? May I say it again, hocam?
Yes.
Is it the point of inflection but stationary mass?
Yes. Yes, we can say that. And Burak, it could also be the point of local minimum or local maximum.
Definitely.
It depends. And this is going to be Burak's part. Yes. Okay, Burak. Okay. I will not tell you about it more. Okay. Let's talk about why horizontal tangents. Horizontal tangents, as we know, they have a slope of 0, right? Okay. So let's find this derivative function, differentiation function, and we find that they are equal to 2 when x is equal to 2 or x is equal to minus 2. And when we put these ones into our function to find their y value, we can find their y value because horizontal tangents means in order to find their equation, we need to find the y value, right? And when you think about it, yeah. And we find that it is y is equal to minus 14 and y is equal to 918. Okay, this part is clear, I guess. Guys, with these videos, I mean, by only watching these videos, it will not be enough to understand this concept. You need to imagine it and solve many questions. Okay, for normals, this is an important part which IB likes, because our rule says, let's take a look at our rule. It says that slope of tangent times slope of normal is equal to minus 1. So, if we, for example, if our slope of tangent is 3, as we find above, and if it asked us the slope function of the normal, the equation of the normal, we would find that it's reciprocal over 1 over 3, and we have add a minus here. It's let's say it is 1. Okay, this is tangent, and this is the normal. It is minus 1 over 3, and you can actually see the why it happens, because if the one the gold color, the yellow line has a sign of positive, but the normal one should have a sign of negative because it's going to go left. It's a decreasing function, but okay, we will talk about it. Okay, let's solve one question. Okay, and when it asks us the equation of the normal to y is equal to x over in square root x at x is equal to 4. I think this is important. And when x is equal to 4, let's find its y value. Okay, you need to find this y value because it's the same logic we get with tangents. They intercept at a point. Okay, when we put these equations, we find that the point of contact is 4, comma 4. Okay, this is the x value, this is the y value. And when we take the differentiation of this, we can see that it is minus 1 over 2, because this is in the denominator, times 8, the numerator does not change, and also we reduce by 1 the power of x, and it is minus 3 over 2. Yeah? And then we can see that we have a slope of tangent. It is minus 1 over 2. If we put 4 in the place of our slope function, gradient function, we found it at above. It's minus 1 over 2, and I made a mistake, right?
Yeah, it was tangent, but I just corrected it.
Yeah, okay, thank you.
You're welcome.
And slope of normal, we take as reciprocal, it is 2, and we add minus. It was minus 1 over 2, so it is 2 now. Okay, so we know that its gradient is 2, okay? And let's construct our line, our equation. And when we construct it, as you can see, it is y is equal to 2x plus c. But we need to find c, right? And we need to pull...
Sorry again, you know that Zoom thingy about our situation. We do not have premium account. That's why it's happening. Again, so you were talking about the normal equation.
Okay. So we construct our equation. It is y is equal to 2x plus c. And this 2 is coming from our slope of normal. Because it's asking us the equation of the normal. Plus c. But we need to pull some data, right? We know that y is 4 at that point, and it is 2. And we know that x is 4 at that point, and it's plus c. And we find that x is equal to minus 4. And at the end, our slope equation of the slope is y is equal to 2x minus 4. That's it, guys. That's it. This is the thing. And if you are like familiar with this, then you will have no problem with these kinds of questions in the future for IB exams. Okay, so Burak, let's go down and
increasing and decreasing curves.
Tell you. Yes.
Hocam, so does it mean that, hocam, I can draw a graph by just looking at its function? Does it mean this one? After that point?
Yes.
Interesting.
Yes.
Interesting.
And also, look, let me tell you something, and this is really important. If you know the intervals when the function is increasing, decreasing, and also if you know the local maximum and local minimum points, you can draw that graph without the help of a calculator. It's pretty interesting. IB asks these kinds of questions, and these questions are around worth 20 marks at least. And we will be solving some past paper questions about them. Okay, so let's see. We know that fx is increasing where our slope function is more than 0, but it is decreasing where our slope is less than 0, when it is negative. You may not firstly understand what it means, but in the first example, it's going to be clearer. Okay, so let me choose pink color. Okay, let's see, and it's asking us the intervals where it is increasing or decreasing. Okay, I have written the answers here, but how can we find it? Any ideas?
Ege hocam, I guess I have an idea, but
yes, yes, my dear student Burak.
I think it was by using the method that you have just stated above. It's already on the page, I guess, right?
Yes.
So let's see how we use the intervals by using the first derivatives, right?
Yes.
Okay.
Guys, it's simple. Okay, firstly, the prior knowledge is, let's draw two graphs, okay? One is from here and one is from here, and this is the graph of in absolute value of x. And I love this graph. I talked about it in the last topic, limits. And we know that, let me draw with a different color. We know that when x is more than 1, okay, it is positive because it's going right. And how you can actually know that? We have this slope equation, and when y is increasing, okay, so when x is increasing, y is also increasing, so it's going to be positive, right? But if you take a look at here, x is becoming more negative, but y is increasing. The denominator will be negative, so it's going to be negative. If you see a function that is going to the right, then it's going to be positive. But if it is going to the left, it's going to be negative. It might confuse you, but if you see the logic here, the slope function logic, then you will have no problem. Okay, so let's solve our example. This was the prior knowledge part. Okay, I will choose gold color. I like it. Okay, so let's take a look at when x is less than minus 1. Okay, it is going to the right, right? I mean, do not look at these arrows here. When x is increasing, y is also increasing, isn't it? So it has a slope of plus, and it's increasing. And this is what increasing means actually. And if you draw a tangent here, it's going to be having a slope of more than 1, more than 0. And when we take a look at the interval minus 1 and plus 2, we can see that it's going to the left, right? You see that it's going to the left because, like, when x is increasing, when x is decreasing, y is increasing, guys. So it is negative. if you see that it's negative, okay, let's draw a tangent here, okay? Let's draw a tangent here. The tangents are less, it's not, I mean, when you take, you might have different perspectives. It could be going to the right or going to the left, from here or here. But if you draw a tangent, it will not let you make a mistake, okay? Let me draw it with a different color. It's pink. And if you draw a tangent, it's going to the left, right? It's pointed towards left. So it's also, when x is decreasing, y is increasing. So it is minus, it is decreasing. And for the second, when x is equal to more than 2, it is also, when x is increasing, y is increasing. So what it means, it's increasing, right? So this is the logic, guys. We don't even have to solve the question, next question, but it is a different question. So let's solve it. I will show you the tricks.
Okay.
Burak, could you go
I just
down a little bit? But, okay. All right. Okay, that's it. Okay. Burak, could you go up? Yeah. Okay. I want to see the
like
the first
this.
example we solved.
Okay.
Yes.
Okay.
I will link it. All right, guys. So, as you can see, let me zoom out. Okay. As you can see, it's asking us the intervals where f x is decreasing or increasing, and we are given the function. Okay, so let's take the derivative, okay? Let's take its derivative, and when we take its derivative, we can see 2 points where x is, where the slope is 0. It is when x is 0 or when x is 2. So there's a sign diagram. There's a thing called sign diagram, and its logic is like this. Let me delete all of it, because I want to show you. Let me draw it with gold color, right, like this. Okay, so let's mark our points, and then when we mark them, let's give this slope function a value where like it is less than 0. Let's say it's minus 1. Okay, when we give minus 1, we can see that the slope becomes negative, right? So we will mark this part as negative, this part. But let's give it a value of 1. As you can see, if we give the slope function 1, we can see that it's also negative. It is negative 12. So it is, let's also give this interval as minus. But if we give this part as 3, let's put 3 here, we can see that this is positive, right? So let's give this interval positive. It is increasing. So we can see that where it is negative, it is decreasing. Also, this is decreasing as well. But as you can see, the slope here is positive. What does it mean? It's increasing, right? The slope function, remember the slope function here, it is increasing. That is the trick, guys. That is the trick, and it's really important. Okay, let's make use of these. Let's make use of these sign diagrams below in stationary points. Bro, could you go down a little bit?
Yep.
Alright, guys. So, we know that we said such things like local maximum or local minimum, and we will learn what they mean. Okay, bro, thank you for showing the diagram below. And let me choose which color, gold color again. I like it. Alright, so we are given a function, okay? And as you can see, we have local max, local minimum, and stationary inflection points. What do they mean? Let's see. We know that the function on the very left side, it is positive, right? It's x is increasing and y is increasing, and it's positive. And when it is between -2 and 1, it is minus. we have a decreasing function there. It's decreasing, that's curve. And when it is between 1 and 3, it is positive. So it is increasing. But also, after 3, when x is equal or greater than 3, it is also positive, guys. It doesn't change. So what you can see, we have -2 here, and when it is increasing and decreasing, we have a maximum point here. And when it is decreasing and increasing, also draw this here, we have a local minimum point. But our inflection means that the behavior of the curve does not change at that point. Because remember this, Burak will also mention it.
Yeah.
The behavior does not change, it is increasing before or after the inflection point. But the slope is 0 there, okay? So it is important to know this, and we call that stationary inflection. Okay, let's go down, and I created a table for you guys. I think it's going to be
very helpful.
Very easy to remember. Yeah, it's going to be really helpful. All right, guys, you can take a screenshot or you can grab your notes from felsefesinde.wixsite.com. You can have an exclusive content for being a member. Yeah. Okay, so I will make use of this in the example below.
Okay, I will show both of them in the same section. Okay.
Okay. Thank you, Burak.
You're welcome.
Okay, so we know our function, right? And it asks us to classify all stationary points. So what does stationary mean, guys? Stationary means when the slope is 0, right? For example, let's draw, let me choose page, yeah. Let's draw a maximum point here, yeah. If you draw a maximum point, and let's say this is our local maximum, and if you draw a tangent here, horizontal tangents, what does it mean? It's slope of 0, right? So we are going to give 0 to the differentiation, the derivative of the function. And we find that at the points when x is equal to 3 and when x is equal to -1. Okay, let's draw our sign diagram, yeah? Okay, when we draw our sign diagram, we have -1 and 3. And when we assign values less than 1, we can see that it is increasing. It is positive, the slope. But if we assign, let's say, 0, okay, let's put 0 here, 0, 0, and it is negative. We have negative here. And the slope is negative. But after 3, let's put 4. And if you put 4, it's going to be positive, yeah? So when we mark them, we can see that, let's draw such the lines, okay? Okay, so when slope is positive, what does it remind you of? The line going to the right? Yeah. And what about the minus? It's line going to the left. X is decreasing and Y is increasing. So, guys, what does it remind you of? Like, does it remind you of this? Let me choose a different color. Does it remind you of this? Exactly. This is local max. And if we do the same for the other point, and it is going negative, and it is going positive, and what does it remind you of? It is
local minimum.
Local minimum, guys. Local minimum. This is the point. You might be confused about like drawing them, remembering when x is decreasing, y is increasing. No, just draw their sketch here. You can draw their sketch by using the line, your knowledge of line, straight line slopes. And that's it, guys. This is the trick. And it's asking the stationary point, so we have to find their y value as well. To find their y value, we just put in -1 in the place of function, not derivative, but function. And when we put them, we can see that it's -1 and 10 and 3, -22. That's it, guys. This is the trick here.
So, again mentioned how we can determine the shape by using the first derivatives. Now I will take on to shape, and I will mention about the second derivatives, how they are used. I was talking to you about this while explaining the concept of higher derivatives. So the thing is that f second derivative tells us about how the gradient of fx is changing. Therefore, I will just divide this into two, divide this page into two. Let's use this color. So, the first one will be the concave up, and then the second one will be concave down. Okay, so you talked us about the sign diagrams and how can they be commented, right? So, let's see these points. Okay, let's say this point is A, and also let's make this point also A. While Ege was explaining it, we saw that for this part, this is f derivative x being greater than 0, right? And this part being f derivative x being smaller than 0. It is decreasing and then increasing. Let me tell you one thing that will make your drawings much easier. If we have such things, for being concave up, and concave up means U-shape, straight U-shape, f second derivative of x is greater than 0. Okay? Because we know that the rate of change of gradient function is increasing. However, in here, let's say this is the part where the function fx has a gradient smaller than 0, and this is the part where it is having something like this, is being greater than 0. So I can say f second derivative x is smaller than 0 over here. And I will be using them in my parts where I will solve some questions. So by the way, we can say that this is applicable for all x being an element of S, okay? Oops. For all elements of being S. This is an important concept. Anything that I'm missing again, alright? We will check for second derivative to identify our shapes in a better way.
I think no. I think no missing points.
Okay. So let me go for an example. Okay. Let's solve an example. Then I will say, let me say, okay, 2x cubed minus 3x squared plus 4x and minus 18. Okay, fine. Let's see. Now I will solve the question accordingly. Let's imagine that there is a question. Identify if concave up or down. Okay, let's see. Let's take our first derivative. First derivative will be equal to, let me solve it by reds to not break the tradition. F derivative x is equal to 6x squared minus 6x plus 4. Right? Yes. Now see the second derivative, 12x minus 6. Again, this reminded me of something that you have just mentioned. I can see that this can be written in the form of 6 in parentheses 2x minus 1. Can't I draw an, how can I say, diagram about this, sign diagram about this?
Yes.
Of course I can. Of course I can. let's come here, let's draw a sign diagram just like this. And when is it equal to 0? When is it equal to 0? Let's find it. 1/2, right? At 1/2. 1/2. Now, what I suggest you is that this is for d square y over dx square, by the way. Okay. Just try to identify by substituting 0 and 1 into equation if it is positive or negative. So when I substitute 0 here, 0, it is 6 times -1, so -6. So here on the left hand side I have a negative. Those values are negative. Now let's switch to the right hand side. Let's substitute 1, which is greater than 1/2. When I substitute 1, I see that I have 6. So this point will be positive over here. They will be positive over here. So I can see that this means that here above at the points where our results are above 1/2, here it is concave up, because in the rule right here, didn't we say that if our second derivative value is greater than 0, it is concave up, and here it is negative, so these parts are concave down. What does it mean? Concave down looks something like this, and concave up looks something like this. And again, do you remember, they don't have to be complete. They don't have to be complete. For example, if we are thinking about, let's say, an x cube diagram, okay, x cube, let's say, just like this, right? So I can say that this part is concave down. Concave down. However, this part is, the other part is concave up. You can imagine just as if it was continuing like this, okay? You can just imagine in that way. It was going concave down.
Could I add something else?
Yeah, sure.
Guys, when x is equal to 0, it is point of inflection, but it is both, like before 0, it is increasing function, and after 0, it is also increasing.
Yeah.
But they are concave down and concave up, so do not confuse those concepts.
Definitely. Let me just divide it so that it doesn't confuse us in the notes section. Okay, so my second concept is inflection points, because again, for example, what happens if my second derivative is equal to 0? Here it is 0, right, at 1/2. This is a question, and this is a great question. Inflection points. So we have two types of inflection points. The first one can be set to be stationary point of inflection. I will not write the all parts. So what is a stationary and what is a non-stationary or dynamic? Can we say dynamic as well?
Yeah, I think, why not?
Okay.
Our teacher told us also that.
Yeah. So non-stationary or dynamic. So I will just draw you diagrams, okay? Draw you some diagrams to show you that. Let's say, or just something like this. Okay. Let's imagine that we have a graph like this. Okay. And here I will draw another one for you to show you something else. Let's it be like this one, okay? This one. Let's say this is a point of inflection, okay? This is a point of inflection. Now, in a stationary point of inflection, the tangent at point of inflection is horizontal. tangent is horizontal, meaning that the tangents, okay, here, tangent line. Hence, can we not say that our first derivative sine diagram looks something like this? Let's say it goes on like this, and this is f. Did my OneNote again crashed? Yes. Please, iPad Pro. Just, I'm reminding you once again.
We are open to donations, yeah?
We are always open to donations.
We are going to start our Twitch live streams and accept donations, yeah?
Yeah, actually it would be very nice. F derivative x. So, okay.
Gülşah Hocam, do you know someone who could be a sponsor for an iPad Pro for better streaming experience?
If you know, it will be very helpful.
Please, guys, please.
Okay, so this is our sine diagram. Why? Do you see that? To have a horizontal tangent line, my curve was decreasing here. It was a decreasing curve. The gradient was decreasing. And also it's here decreasing as well. So f derivative x sine diagram looks like this. And my f second derivative x sine diagram looks something like this. I will draw another one very quickly. Okay. F second derivative x, and I will say this is point A. I will go on like this. Now, something important. This part is negative. This part is positive. Why? Again, you can see that on the left hand side over here. You see that, right? Over here, yes. It is concave up. I can just completed it like that. However, above the point of inflection, it is concave down, because tangent line is horizontal. And we find inflection points at points where f second derivative is equal to 0. Therefore, our A is a point of inflection, definitely a point of inflection. Now, you may say, okay, what changes? What changes in, how can I say, non-stationary point of inflection? In non-stationary point of inflection, let's say this is the point of inflection, okay? Point of inflection. Can you see that my tangent line will not be horizontal at all? Is this horizontal again? Does it look horizontal?
No.
No, right? This is my tangent line. Therefore, I will say my f, not this color. Oh, I guess we ran out of time once again. We will just, sorry once again, as I said before, if you have anyone who knows Zoom Premium account who can provide that, we are always here. Okay, so I said f derivative x sine diagram should look something like this. So in here, actually we will have more than that, okay? More points. Let's say we will have a B point, then we will have a C point. Actually, I should have written them here, B and C. And they should be, for example, here it is negative and positive here. Now let's see that. Again, you can see that over here it's increasing, right? Over here it was increasing. Let's say to this point B, okay? This was point B. It is point B. Then let's say this is point A. X is equal to A and X is equal to B. And let's say this is the point where it's equal to X is equal to C. You can see that. So up to B it was increasing, then from B to C it was increasing, and then it went on just something like this, but sorry, this is positive, of course. Then it increased. So it is right in the middle, okay? Therefore, our f second derivative x sign diagram looks something exactly like this. F second derivative x, and I will have the point A over here. Now, do you see that it is negative over here and positive over here? Because I see that this is concave down, right? Below A, it is concave down, but above A, A is, after that point, it is positive, so it is concave up. Did we understand the difference? In f first derivative sign diagram, A remained at a point which is here. This is the point where A belonged. A was somewhere here, but it was negative, or it could be either positive as well. Anyhow, the tangent line is not horizontal at point of inflection. This is all we can say. Therefore, I will just write one more statement. Stationary point occurs if f derivative a is equal to 0, and it is non-stationary if f derivative a is not equal to 0. Again, did you realize it? In my sign diagram, a, it's a point of inflection, right? And is it 0 at A, at point A? Yes, because it is stationary, because here tangent line is horizontal, meaning no gradient at all. However, if it is non-stationary, of course tangent line has to have a gradient. Since it is not horizontal, therefore the derivative function by substituting a should not be equal to 0. Therefore, again, may I make a summary of that last part?
Yes, please, and it's going to be very useful and helpful.
So I will say summary. I will use a Venn diagram, okay? I will use directly a Venn diagram. Let's say, come to here. Let's draw two circles, one being like this, and make the other one like this. So, I will write for this part turning points, okay? Turning points. You mentioned about turning points. Then I will make this part non-stationary inflections. So let's think about it. What is in common between those two? Stationary inflections. Stationary inflections. Okay, like this. Did you see? Because at stationary points, first derivative is equal to 0. At inflections, f second derivative is equal to 0. So what could be come together between non-stationary points and turning points? This would be a good Venn diagram to explain our concepts. Yeah, definitely. Okay, so again, now bro, it is time to go with understanding functions and their derivatives. So this is a summary, okay? I will just read through it and take notes if necessary. You said the sign of f first derivative tells us if a function is increasing or decreasing, right? I will just write it like this: f derivative x, increasing, decreasing. Okay, like this. The second point, the zeros f derivative x is equal to 0 shows us stationary points. Stationary points. Then the sign of f derivative f second derivative fx tells us shape of function, meaning what? Concave, up or down. This is what we learned from here. Then f second derivative x being equal to 0 tells us what? Point of inflection. Point of inflection. This is the point where the signs for f second derivative is changing. Therefore, you may just be asked these questions in the very last part, right? In the very last part.
Yes.
So, again, may I just talk about our last thing for today? This is the last thing. L'Hopital rule. L'Hopital's rule. L'Hopital's rule. This is an easy concept, right? It's not as hard as its name.
No, it's very easy.
Yeah. So we know that when we were talking about limits, okay? When we were talking about limits, there could be some situations. For example, let me give you an example, okay? We will understand it by using examples. Let's say our fx is equal to sine x over x. This is the most common example, that's why I gave it. And you can see that. Let's find its limit, okay? Find limit as x approaches to 0 sine x over x. Again, can you solve this question just as we did it in yesterday? What would it be? Limit x goes to 0.
We actually like sine x goes between 1 and -1, and when x is approaching 0, and it's like it's going infinite, I guess, and it's
actually to the 0. If it was another, like it, what happens if x goes to 0 and sine x? What would happen? It would go to 0, right? So let's say 0, and x is already going to 0, 0 over 0. Can we have such a situation? No, because this is indeterminate. You have to write it definitely in this way in your IB paper, and you will say that now it's time to use L'Hopital's rule. He said there are indeterminate cases, okay? Indeterminate cases. What are they? If you are solving a limit question, and if you came across a situation like 0 over 0, or let's say infinity over infinity, or let's say for 3, 0 times infinity, this means that you have an indeterminate case. You have an indeterminate case. Therefore, should I write examples for them again, or should I just skip them?
I mean, let's not make it too long.
Yeah, I mean, if you have this case, okay, for example, in sine x over x, we saw that 0 over 0, it was the first case. So if you have those kind of cases, L'Hopital said that you can use the derivative. You can take derivative of both numerator and denominator by keeping the same range and keeping the same limit. So let's say for limit x goes to, let's say, a point A, and we have a case where fx over gx is giving us an indeterminate result, okay? Results. Therefore, L'Hopital realized that it is as same as saying limit x will approach to a f derivative x over g derivative x, right? Now again, what would you do if this was also indeterminate?
I would apply another L'Hopital.
What if indeterminate just go on with more L'Hopital. So until you reach a unindeterminate results, you have to apply L'Hopital rule, right?
Yeah.
And there is one more important thing. We solved the question yesterday. Maybe you can remember it. It was like sine x over x cubed, the one that we discussed previously. It is impossible to reach to an unindeterminate result. Okay? You cannot understand this concept. So use your logic while applying L'Hopital rule as well. This will be very important. So should I solve a question about this?
Yeah, let's solve.
Okay, so here is an example. Let's say solve, let's say limit x will go to 0 and we will have 3 to the power x minus, let's say 1 and over x. So let's use firstly traditional methods. I am using traditional methods. Limit x is going to 0, approaching to 0, 3 to the power, let's write 0 over here, minus 1 over 0, right? What happens is that we will come to know that 1 minus 1 over 0, meaning 0 over 0. Is it one of those undeterminate cases? Yes.
Yes, definitely.
Indeterminate. Therefore, I will just write L'Hopital. I'm just abbreviating it. Okay, so what we will do is that we will say that limits with red, let's go on, or let me write with orange to understand that we are switching between the methods. So limit as x approaches to 0, it will be as same as d dx of 3 to the power x minus 1 over d dx of x, right? What will it be equal to is that limit x is going to approaching to 0 and I am taking a derivative of both numerator and denominator, keeping my limit exactly as same. Therefore, I will come to know that this will be equal to 3 to the power x ln 3. Am I right? And below I have only 1. Everything is correct, I hope. So now let's substitute our 0 inside. 3 to the power 0 times ln 3 over 1. 3 to the power 0 is 1, right? Ln 3 over 1. So is this indeterminate again? No. It was not indeterminate, so we came to know this. If it was indeterminate, apply it once again, until you reach a result, but use your logic as well to not to make any mistakes. So we came to know that it was ln 3. I took the derivatives of both numerator and denominator after realizing that it was indeterminate, meaning 0 over 0, infinite over infinite, or 0 times infinite. Therefore, Ege, shall we call it a day?
Yes. Let's call today because I think our viewers are tired.
We are also tired.
Gülşah Hocam said that she is going to study some HL physics.
I saw it now. Oh, that was tough.
Yeah.
That was tough. Thank you very much, everybody, for being together with us. And it is interesting that we do not have any mathematics HL people here. But it was a great pleasure to be together with you. So follow up, we will be talking about calculus episode 3 tomorrow about integration, right again? If I'm not mistaken. Our economics video will also come up. So please follow up on Twitter, Instagram, our website, Felsefesine Kart, everything. We will be sharing our notes once again. It was a great pleasure. Do not forget to solve past paper questions, make your own revisions, and if you would like to attend Felsefesine team, please do not hesitate. You can just contact us from all those platforms, and we will be very glad to see you together with us. So, anything you want to add again?
No, thank you guys for taking your time.
Definitely. So now it's time for us to drink a cup of tea. Thank you a lot. See you. Bye bye.
See you guys.